there we go. पहले वो दो सीखो। Starting with the homework.
Okay, so today we'll discuss called Jake's model. Book is read by W.C. Jakes and it's available in the library. Are there multiple copies available? I borrowed one. Not I will order one. Okay. So if you are interested in learning about elementary aspects of wireless, this pocket. In fact, for a long time this was the only textbook available for volume is not very high when I speak. Okay, you can increase the volume. Okay, so let's recap what we had done last. We came up with this app delay line model for the wireless channel. Baseband we resolved the key space channel. Resolved into an FIR channel. Of tabs. Okay. So resolve these tabs at key space. We end up with channel tab set facing here. These are multiples of capital T because system is operating it. The system is operating sample rate, which is starts with 0, this should be T, and so on. Okay, and we did explain the relationship between the original analog channel and the time channel that we observed. So a good model is that we would be using widely. Well, we don't want to model the channel piece because the receiver is going to construct that channel. What we need to model is the original analog channel that comes at tau equal to 0, tau equal to tau 1, and so on, so forth. So when you transmit a signal, it is converted with this original analog channel, and then you operate at some rate at the receiver, and then it gets resolved into a key space bandwidth of the system. We talk about a narrowband system where the entire equivalent channel appears as a single tab with relative. Very wideband system, you can resolve it into a number of resolvable. Okay. But we did not mention anything about how to model these tabs, especially. Okay. Then you would be asking the question, well, at what I mean, how do you in fact model the original analog channel? That's a question. Conduct measurements, of course, whenever you conduct measurements, the equipment itself has a resolution bandwidth. Therefore, you can only observe the channel some minimum spacing, right? So, nevertheless, we assume that the resolution bandwidth of the equipment are. Assume that we can observe the channel at very fine bandwidth. Okay, and in between, so this tab itself might be a sum of several rays falling in around tau equal to 0. Therefore, this trap itself might have Rayleigh distribution. One plausible model. Original channel has a number of taps, and these taps are occurring at different delays. And you can possibly model these taps. The particular tap here itself might be some collection of a number of links. That is the case, then we can model them as individual. Okay. That is the case. Each one of the steps can be modeled as, for example, this step can be modeled as complex Gaussian process. Okay, and a given variance. Talk about a complex Gaussian process, then there could be a time evolution also. Let's hold on to that for a little while. Let's assume that let's ignore the time variations of time being. But as a complex Gaussian random variable with 0 mean and some variance. And this could be modeled as yet another complex Gaussian random variable with certain variance, and all these random variables can be modeled as statistically independent of each other. So that's just a model. Okay, that's one possible model. So what I want to discuss right now is how do you simulate a multi-path channel profile? Signal that is simulation. How would you model? We talk about one particular simplified model where we can possibly model this as a complex Gaussian random variable with 0 mean. All these steps can be modeled as but then we are also interested in modeling the time variations in the channel. The taps, and these taps could possibly vary in time. Taps could possibly change with time. That is because of the movements in and around the receiver, or the receiver itself might be. Okay. So if that is the case, we need to come up with a model the time variations. Okay. So let's just focus on that. So we'll come up with so-called X model to model the time variations in the channel, and we can simply model all these taps as time varying channel taps following that particular. So let's just focus on a single tap for the time being. Okay. So essentially we're going to talk about a narrowband scenario. Talk about a narrowband system with single tap channel. That's what we're going to talk about, with allowing for time variations. Before we proceed into that model, let me introduce I'll first talk about the phase velocity. Then we'll to talk about. Okay. Remember, electric field E is equal to E naught raised to minus R again e to the power of j minus. When we talk about this electric field, we omitted e to the power j omega t in the previous lecture, but I'm introducing omega is the okay. But alpha is the attenuation constant, and beta is the okay. Phase velocity as v corresponds to the velocity the wave must travel in order to keep the phase constant. Okay. So therefore, we must have omega t beta r a constant. Differentiate on both sides. Right? Lossless medium beta is equal to omega into square root of okay, that we discussed last time, right? Here mu is the magnetic permeability. Okay. Therefore, the phase velocity Vp is equal to 1 over of mu multiplied by okay. In the wavelength lambda equal to okay. Okay, now we are interested in the phenomena of Doppler. What is Doppler? Vehicle is moving at a given speed. A signal at a carrier frequency, let us say f, as of the movement of the vehicle, third frequency will be Erase this. Have you taken the notes? I'm not going to get into the electromagnetics part of this excessively, but just touch upon it a little bit. Not very extensively, but the treatment generally begins with electric field and magnetic field, and then it goes into. Okay. But otherwise, we can always start with the general path. Anyway, why are we discussing Doppler frequency here? Whenever the vehicle is moving, I receive signal, some collection of many time variations, random, random amplitude and uniform phase. Then this amplitude itself changing time because of Doppler. Okay. In fact, measurements conducted its range. Thankfully, the models we are going to develop closely agree with the statistical models agree with the statistics obtained from the measurement. So, for example, before we go into Doppler and just draw this picture, if I take measurements at 836 megahertz, well, of course, I'm just drawing this picture. F equal to 836 megahertz, and this axis is time, and this axis would be the RMS value of the received signal in decibel. Signal strength in decibel. The waveform recorded, let us say, for some 1.8 seconds, 6 to 2 seconds. Variations, let's say it is at 0 dB, then some variations like this, you can observe. Some of these depths, fade depths, can go as low as minus 30 dB. What's happening is that the received signal envelope, of course, when we talk about baseband signal envelope, sometimes it is higher than 0 dB is what? Unity, right? Sometimes it is higher than 1, but quite often, yes, I didn't write. Okay, that shows that it is less than 1 all the time. Quite often, it takes values below 0 decibel level. So, fades as deep as minus 30. What do you mean by fade? Just This is the signal envelope. It has been observed, okay? So now we want to come up with models to explain this. Take all the time samples and plot the distribution. What would it sample and take another sample? The velocity is miles per hour. That was for a moving receiver. So obviously, if you look at a vehicle moving at 40 miles per hour, the variations would be even more rapid. And if it is moving at 3 kilometers per hour, you would expect the variations to be something like this. Variations are rather slow. So you will see it. This is the signal amplitude measured in decibels. But you may say, well, what if the vehicle is stationary altogether? But still you would experience changes rather slowly, because although the receiver is stationary, but the surroundings will have a change, and that change manifests as an equivalent Doppler or speed. Break the notion of Doppler and speed in a minute. And we'll discuss what is really. Okay. So let's take a hypothetical scenario where there is a transmitter, then there is a user located on some vehicle. Okay. Vehicle is moving at speed kilometers per or V meters per second. What is this theta? Yeah, well, this is the angle at which it is incidental. That could be any angle. Okay, the speed of this vehicle will impose an apparent phase velocity What is this apparent phase velocity? Vp prime. Vp was the terminal phase velocity. And since you are moving at a speed v, and this Vp prime is such that prime is equal to Vp minus that be V cos theta. Suppose you may say why it is not plus V cos theta. call that Vp is equal to, was it lambda into then Vp prime is equal to lambda into f prime. Where f prime is the and f is the frequency of transmission. Then we can write f prime as f minus some Doppler frequency fd, where fd is equal to is the Doppler shift. This makes sense? Good there. Similarly, omega d is equal to omega m cos theta, and omega m is theta into d. D is the velocity of the vehicle. And Vp prime is associated with the incident wave. Okay, that is the phase velocity. Okay. How we got this? Okay with this. Huh? Okay, not much in it. Let's make some calculation. Let's take a vehicle moving really fast. D is equal to 72 kilometers per hour, that is equivalent to 20 meters per second. F equal to 1 gigahertz. So lambda would be 0.3 meters. What is FD here? Tell me what FD is. 6.7. That is the Doppler you will see. The higher the speed, the more would be the, or even if you increase the carrier frequency, that would have still increased. Okay. Now, how would this Doppler affect the received signal? That's something we want to understand. Angle, I mean, it's immaterial because we're calculating the maximum Doppler. Okay. Anyway, theta will be taken off. Go to the ground plane. Let's assume an omnidirectional antenna pattern. Azimuth. Okay? And this will be the incident angle. Yes, depending on antenna location. Let's assume an omnidirectional. Yeah, that's a question that was being asked, right? Yes, still there would be. How would you characterize that? Well, the vehicle is stationary. Well, actually, we have to go a bit deeper into the multipath propagation and how Doppler affects it. But just to quickly answer your question, the vehicle might be stationary, but the surrounding objects have some movement, and the received signal is not just a line of sight signal. I mean, this is just a virtual representation. Okay. So, I mean, we're not really talking about multipath propagation here. I'm just talking about the notion of Doppler. But if you have multipath propagation, you have reflections from a local scatterers. Okay, and when this vehicle moves, obviously, even though movement is on the order of a fraction of wavelength, still the received signal undergoes quite a bit of a variation, right? Because what you receive from here and what you receive from here, even a few centimeters apart, can be quite different. Okay, so if the vehicle is stationary, still the local scatterers would experience a change in time, and that manifests as an equivalent Doppler. Okay, we'll see that. Go through the model. No, Doppler frequency shift is defined as something related to the vehicle speed. Let's leave it this at this as it is. Now we'll go through a model that models Doppler, that combines Doppler and multipath propagation, and then revisit it. So, I mean, the answer would not be visible on this board. But give a quick answer, yes, there would be an equivalent Doppler. That's not visible here. Okay, so we'll have a mathematical development now for the so-called JX model. Okay. There's this. Okay. Okay. We'll have an expression that represents the received field as a superposition of number of plane waves. Okay, that is real part of some signal t of t e to the power of j omega c t, where omega c equal to 2 pi fc. Fc is the carrier frequency. Previous notation we called it F, but we switched to FC here. FC is the carrier frequency. Could be given. Okay. And what is T of T? Obviously, T of T is the low pass baseband form. Okay. And T of T, you will write it as from E naught summation of a number of signals n equal to 1 to capital N, some constant Cn of J M T cos alpha n plus C, where the Cn constant square is equal to P of alpha n alpha Okay. What is omega m here? Omega m is Doppler frequency. That would be beta V. That's the maximum Doppler frequency. So this would be beta V cos alpha n is equivalent to the incident angle. Alpha n is equal to the incident angle theta in the previous expression. But then the assumption here is that mobile located here, there are scatterers from all directions. What would be the angle, incidence angle? Well, the incidence angle is different for different rays that are arriving here. There is no single ray coming from line of sight. There are different rays arriving here. Each would have its own incidence angle that is alpha. Okay. So this part, let us say omega m is 0, then it is very similar to what we had before. What it was? Sum of Cn. We had an e raised to j by n. Remember that? Remember the derivation for? We had this derivation where we took sum of several rays, each with an amplitude Cn and a phase. Okay? Now what is extra here? We are introducing the part due to Doppler. Make sense? The model makes sense? We had sum of several rays, each with an amplitude Cn and phase phi n. So, but then there is a component induced by Doppler that would be omega m T cos alpha. So there will be 3 parameters for each phase coming in. Sum of several rays, and you will be asking, what is Cn square for each ray, then it is the amount of received power. Let's say you have a antenna pattern which is a function of alpha n. The power received in an infinitesimal angular region alpha d alpha. Cn square is equal to, what is this power? Well, in the previous model we just called it amplitude of different rays and we assumed them to be random. Here we just call them the amount of power received in a infinitesimal angular bit d alpha, and p alpha n could be the radiation pattern of the receiving. If it is omnidirectional, well, right? Take a moment and just look at it more. Now we will assume that the arrival angles are uniformly distributed. That is, these alpha n's are uniformly distributed. Then d alpha will be 2 pi by n, where n is the number of rays. Okay? Of course, in the limit as n becomes very large, then d alpha becomes infinitely small. Therefore, Cn square will be, if that is the case, Cn square will become d alpha is 2 pi by n p of alpha n 1 over 2 pi, so that it becomes 1 over n. Why is that 1 over 2 pi? Uniform. P of alpha n is uniform in alpha n. Therefore, P of alpha n is equal to 1 over 2 pi. Okay? This part is taken care of. This is beta m is, omega m is beta into V. Okay? Now, how to calculate beta? Pi by B. 2 pi by 2 pi by lambda. That's easy. Okay. So we know beta m, alpha n's are, well, they're uniform, right? The alpha n would be pi small n by capital N, where n equal to 1, 2, up to capital N. Make sense? They're all by n by. Okay, so that's it. We need anything else? Same argument applies to phi of n. Phi of n was anyway assumed to be uniform. Okay, so that would become 2 pi. Okay. Well, now we happily have a model for modeling P of t. Now we have a mathematical model that takes care of Doppler. Now the vehicle need not move. As long as the rays move, that's good enough. So these 4 are 1, 2, 3, 5, or 6, 7. These 7 rays, after let us say you're saying vehicle is not moving, after let us say 5 milliseconds, maybe the surroundings may change. If they do change, then you might see this ray. Get these rays. What did you get? You may get a completely independent value, statistically independent value. The sum of sine waves, and we know that distribution is complex Gaussian with having Rayleigh, with the envelope having Rayleigh distribution. And if you allow sufficient time and if there is enough change in the environment, you may get an independent fade. I mean, by fade we mean envelope of T. Let's see how we can interchange Doppler with vehicle need not physically move. But if it does move, then I might have, maybe I'll move a few centimeters, then I have another local scatter ring it really depends on by how much amount this moves from here to here. If it moves by a little amount, then pretty much we'll have same type of rays contributing, maybe with a slight phase difference, slight amplitude. Then you can expect this T of T1 is T of T2 because it has moved from here to here in some time T, they can be correlated. But if you allow for sufficient time T, then they may become totally uncorrelated. Since we have a Gaussian process, uncorrelatedness implies statistical independence. And they are zero min process. A nice thing about this is that it takes t seconds to move from here to here. On the other hand, think of placing two antennas separated by a distance d and taking a measurement at the same time. Well, that is the diversity spacing we talk about in mind. Two antennas separated by d, and when the d is sufficiently long, sufficiently large, these two become uncorrelated or statistically independent. Normally, at these mobile radio channels, if you allow lambda spacing or lambda by 2 spacing between them, then you will have more or less independent phase. How Doppler and distance can be interchanged? Right? This is omega m, right?
Same for all the rays.
I think you really need to take a look at this. Omega m is beta into v. There is nothing that is ray dependent here. Omega m, that is the maximum Doppler spread. But only thing is that this v, if it is large, it's going to cause more variations. If it is small, it's going to cause t. This v, there is a multiplication with t. So the larger it is, the faster the changes are going to be. Okay, so that's how the speed plays into a role. So these time variations will be faster if v is small. In the limiting case, when v is 0, well, there is no time change. The only function that is the only part that is a function of time is this. If v equal to 0, changes, right? As if nothing. Of course, what we say is that even if v is equal to 0, there will always be a change in the environment. That manifests as an equivalent. Right. This is what is moving. These are the incident waves. All of them would experience more or less the same Doppler. Angles are different. Angles are different. I mean, the angles are different, but this part is the same for all the rays, right? So we have basically generalized the simplified Rayleigh fading model to include Doppler here. Of course, what we have not included here is the coherence, bandwidth, and the multi-path delay spread. That has been taken care in the wideband channel, right? I have to bring it here. But I will talk about what is the effect of multi-path delay spread on the multiple path delay spread. How would it affect if you send two waves at two different frequencies? Let us say I send one wave at omega c1 and another wave, let us say 300 kilohertz apart, omega c2. Will they experience the same things? Frequencies. Then fading on omega c1 and fading on omega c2 correlated or uncorrelated depends on how much multipath delay spread that is basically how two different frequencies get affected because of multipath propagation. Then we can talk about the notion of coherence. That's one. That is a part of the picture. The other part is how does Doppler affect the time variations in these caps? Right now we are kind of decoupling them. Phenomena happening here. Yes. One is there is Doppler spread, and the other is one is Doppler, the other is delay spread. Okay. You may say, well, all these rays are coming in, and then there may be a time difference of arrival in these rays that may manifest as delay spread. That's a valid point. but we are trying to come up with very simple models. We assume that all these rays are coming in within very time delays between them are very, very small, and therefore they manifest as a, those delays manifest as a phase here. Okay. So basically we are not able to resolve all these paths, and we are considering a very narrow band system. It is a narrow band system. The entire model is for a narrow band system. If you want to scale this to a wide band system, you can complicate this model. Okay, starting from this kind of a model by adding some extra multi-path related terms. But otherwise, what I would do is, we already have this wideband channel model, right? So come up with. All I would do is, in a brute force manner, each tap I'll assume that it is fading. There are time variations down by the graph. Let's keep that simple model. Two ways to handle it. One is, we take this model and we can superimpose the effects of delay spread into this model. Then we can jointly analyze the effect of delay spread and Doppler at the same time. But on the other hand, instead of complicating this whole exercise, we'll just assume that each tap is fading independently, and Doppler that is causing these variations. But of course, it would be the same Doppler we are assuming for each tap. That may or may not be. Sometimes different taps may, but they're not. All the taps are going through same tap. Okay. Let's return back to this narrowband model. There are a few things that we want to understand in this narrowband model. We have T of T1, then we have samples T of T2, and so on, right? Now we want to understand the what is the autocorrelation of this T of T, this process. Now we can think of T of T as a complex Gaussian process, right? Already showed that it was complex Gaussian. Absence of. Now we can think of the autocorrelation between T of T1 and T2. And in other words, we can formulate the autocorrelation function R of tau with respect to the value of T of T of T plus tau with a conjugate sum. We can think of. Now, to write this, we are sort of make some assumption that this is a Whiteson stationary. That this is a Whiteson stationary complex Gaussian and Whiteson stationary complex Gaussian. We can derive the autocorrelation function for this. T of T is described, right? And all the random variables involved are also very well described. So finally, the autocorrelation R of tau would be a function of what? Tau and then omega m, because omega m is also parameter. It's a function of omega m and t. Before we do that, I'll just give you a simplified model. I want you to simulate this T of T for a given carrier frequency and Doppler. I will give you the carrier frequency. FC is 1 gigahertz and is something like 100 per hour. Okay. And I want you to plot T of T. Plot magnitude and phase of T of T and plot the autocorrelation function R of tau and compare that R of tau to the theoretically expected one. That will derive. Okay. In addition, you can make some simplification on this T of t. This T of t can be written as I'll just give the expression and I want you to what is the square root of n? Cn, right? Cn square is 1 over n. Cn will be and I will introduce the factor square root of 2 that normalizes the energy to unit. Okay, introduce artificial. So I can also put it here. Okay. And the ray, sum of rays goes from n equal to 1 to n naught. It's not all the way up to n. We have 4 terms. Of j omega m t cos alpha n plus e to the power of minus j plus phi of minus n plus phi of capital N Okay, I'm not going to show the equivalence, you can figure it out. And n naught is equal to 1 over 2 n by 2 minus 1. If you are going to implement this in DSP, it's best to reduce the number of summations, right? Because the complexity increases as you have more terms in the summation, right? So if you want to implement it in DSP or an odd way, it's good to implement this. Okay. So I want you to implement this. I want to implement this and choose n equal to 8. Anywhere from 6 to 8, central limit theorem kicks in. What is this? Not n naught, it is n. N is from 6 to 8 and n by 2 is an odd integer. Okay, so I will not go into the specifics of okay. Now let's compute the autocorrelation function. Autocorrelation function. Yeah, well, you can look at the power spectra, but real system. What is the slot length, GSM, something like half a millisecond or something. Slot has data, and everything in terms of a slot. Then there is this data, then there are pilots, and then data, and everything is spanning on the order of something like a half millisecond, something like that. And it's a narrowband system, 200 kilohertz bandwidth. GSM is a narrowband system with 200 kilohertz bandwidth. And there is a reason why we come up with these models, and there are practical implications. Okay, we'll look at the effect of bandwidth later, but now the vehicle is moving at, let us say, 20 kilometers per hour. Would you experience an independent channel when you look at samples taken at 0.5 milliseconds? That is the case. Take two samples, and if they are statistically independent or uncorrelated, the minimum separation times of separation required is called the coherence time of the sample. The time separation, the minimum time separation for which two samples, of course these are complex samples, right? We should take the, obviously we should take the perhaps the envelope, right? The envelope of signal become uncoherent, and that is called the coherence. If the coherence time is 0.5 milliseconds, then we are in deep trouble. Is that? Well, there is only pilots in the middle, there is data and there is data. You measure the channel here, and you assume that the channel is the same before and after, and you try to demodulate. But if the coherence time is on the order of 0.5 milliseconds, then we are in big trouble. We need to ensure that this time slot length is much smaller than coherence time. Then we can happily assume that the channel is nearly time invariant over the packet duration of interest. Then we consider as a time invariant system. Of course, when you build a system, obviously you can't design it for one speed. At 3 kilometers per hour, maybe there are hardly any variations. But then you have users stationary talking on the GSM phone, and then there are high-speed bullet trains. They are moving at 300 kilometers per hour. We can't design, so you have a design system for a typical speed like the 3 kilometers or 30 kilometers or 300 kilometers per hour. We can't design systems for 300 kilometers per hour because only 5% of the time maybe you're using that. So you design it for a target speed that is 30 kilometers per hour, a vehicle moving, and at very, very high speeds, maybe you employ some and receiver thing and make the system operational at 300 kilometers. To optimize the entire system performance. To understand what is the effect of Doppler on this entire system, we do need to look at the autocorrelation function R of tau, and that is a simple function of omega and tau, and it has a very elegant expression. If you know what it is, then given omega and tau, you can quickly say what is the correlation. If the correlation is low enough, well, we're happy and good. And the tau is nothing but slot length. And we see, well, how much correlation. Well, if the correlation is 0.1, well, it's an engineering. Okay, so we'll just close this with the derivation for R of tau. We're not going to spend a whole lot of time on that. To have insight of what it is. So, well, actually, we will look at so looking at the baseband correlation. We'll look at R of tau, that is the expected value of E of t, the original electric field, which is a real signal, right? E of t plus tau. Okay, and that turns out to be constant naught by n cos omega c tau times summation. For now, I'm writing summation over n naught cos omega m tau by small n by n 2 cosine. Well, this is a something. This looks something like some function g or tau multiplied with cos omega c tau. And this g of tau can be shown to be some constant b naught, Bessel function of 0th order omega m tau. That's what we're really trying to do. So we don't care about this omega c part because it's in passband, right? So what we are interested in is the autocorrelation function of the low pass baseband part. That is a function of that is the Bessel function of J0 omega m. Huh? Oh, it's just a constant, somewhere it comes. Okay. Okay. Don't worry about that J0. This J0 of x is defined as 2 by pi sin of x cos alpha d alpha. How do we get this then? Well, this is what we have, and this is together with this part is g of tau. But it doesn't look like a Bessel function, does it? Look like a Bessel function? Well, this is sum of some waves, and this is not quite in that form. Okay, but what we can do is, right, we can extract that two times, take this two out, the two outside, okay? We can expect that this part we expect that. Well, we're approximating the it's a discrete. We have a discrete approximation to the continuous integral. Does it make sense? Just look at. I have to replace that integral in the set of discrete component ranging from 1 to n naught. Of course, well, actually there is a 0th term also, right? Cos omega m tau x is omega m tau, alpha is replaced by 2 pi n by n ranging from 0 to n naught, and 0th part comes out. Huh? This is a discrete term, so you do end up with. Okay? Anyway, that n and this other n will cancel out. That not by n by 2 and 2 by n will cancel out. Then the whole expression will be independent of n. Because in the limit as n tends to infinity, this should hold, right? Okay? The approximation, that is the will continuous case. Well, what is the point here? The point is r of tau is like a Bessel function which is parameterized by omega m. Okay, and there are a number of simplifications and modifications made to this model over time by different people. Better and what I want you to do is first simulate T of capital T of T and then calculate the autocorrelation function numerically in MATLAB. Of course, you might want to calculate the autocorrelation function for the discrete base time function, and then compare it with the Bessel function not omega and tau. Obviously, because of Doppler, if you look at the power spectral density of the transmitted frequency FC, it will shift, right? Your power spectral density would be around FC is the let's write around FC. It will be like that. FC plus epsilon. Okay, so the shape need not be uniform. Depends on actually the antenna characteristics and many other aspects, but you will encounter change in this spectrum. Not what we want to view, but it is this correlation between the time samples is really. When does the Bessel function hit the 0 or 0? Point? 2 point. That means, so if you want a 0 correlation, omega tau is point. What it is? So then you have to choose tau equal to less than that, right? Make sure. Well, you can't choose tau equal to 0.4 by omega m, But this is when the samples become statistically independent. If you want to design a slot, then it has to be much less than. But on the other hand, if you send data in many time slots, this slot 1, 2, and these are slots and this is a frame. And if you code the data such that it takes within a slot, the variation is very little, but slot to slot there will be slow variations. And at some point, at tau equal to 2.4 by omega m, you will see an independent fade. That would be a good thing because you will observe a number of independent fades. Of course, they're slowly changing. Maybe 2 fades, 3 fades, 4 fades over a frame of, let us say, 20 milliseconds in duration. And speech usually we code it over 20 milliseconds duration. And within these 20 milliseconds, if you observe many independent fades, you can apply channel coding over these fades and get what is called diversity. Okay? So for example, if you have an independent fade and if you repeat the data over these independent channels, and at the receiver if you combine these repeated data, then you get sum of squares of R1 square, or if they're envelopes, R1 square plus R. Well, I mean, you're not going to repeat all the way, but if you repeat over sufficiently long duration, some spacing, then you get what is called a diversity. That's a simple repetition. You can advantageously exploit the variations, because the variations are there, and you exploit it for diversity benefit. The reason is that if one of the amplitudes goes through a null, maybe the whole slot is lost, but maybe after 10 milliseconds, you'll have a peak. It's a good thing, right? At a given time, you have a deep fade, you lost a slot, but after 10 milliseconds, you may have a peak because of Doppler. And if you repeat your data or if you code them across these various slots, then you get what is called diversity. So you need not lose data on all the slots. It's a good thing. But on the other hand, the duration of the slot should be small enough so that Doppler will not create too many channel estimation. Okay.
Very less than
Much less than. You can compare for GSM, the slot duration is 0.5 milliseconds. You can check out for, let us say, 30 kilometers per hour at 800 megahertz. You can compare what should be come. Calculate and see it later. 0.4 by omega and what would it come to? At, let's say 800 megahertz or 1 gigahertz. So roughly speaking. Nanosecond. Velocity is take the speed of light. You take free space. Okay? You know lambda already, right? 0.3. Take that example. Calculate and tell me what. Omega tau is basically 2 pi tau by, V should be the not velocity of light. V should be the speed. take whatever it is. I'll take it 10 20 minutes. Huh? 11 milliseconds. So GSM slot is 0.5 milliseconds. So that's almost like makes sense. And then in GSM, the speech, you can tolerate a delay of up till 20 milliseconds. You know that, right? As human here, beyond 20 milliseconds, it starts to perceive the gaps. So you can take 20 milliseconds delay, you can tolerate. Actually, buffer up to 20 milliseconds. Each 20 millisecond frames are acceptable. That is the case. 20 milliseconds, how many fades you will expect? Can't say for sure, right? It's a random phenomenon. The occurrence time is 11 milliseconds, you said. So we start at some fade, and after 11 milliseconds, let's say you have an independent fade, after another 11 milliseconds, 3 fades. So you can have a diversity out of 3 actually. So you can't say for sure every time you'll have 3 sometimes. Code over 20 milliseconds, you get a diversity of order, either 2 or 3 or 4, depending on what it is. But on the other hand, the slot length should be much smaller than 11 milliseconds. Let's take GSM bandwidth. Bandwidth is 200 kilohertz. Okay. And what is the symbol period for 200 kilohertz? Okay. So in GSM, bandwidth is 200 kilohertz. What is the data? What is the value of T? 1 over T is 200 kilohertz, let's say, and T would be huh? What is that? 5 microseconds. Okay. So that is the rate at which symbols are transmitted. Okay. And the delay spread in typical urban areas is on the order of 0.2 microseconds. What is delay spread? Do you know what is delay spread? Delay spread is impulse response, right? Tau equal to 0, tau equal to tau 1, tau equal to tau n. Delay spread is the RMS value of this delay, but let us say the maximum is 0.5 microseconds. This 0.5, let's take it as delay spread. I mean the maximum, the last multipath component comes at 0.5 microsecond. Okay, if that is the case, given T is 5 microsecond, okay, so 0.5 microsecond is like what? One data symbol is 5 microseconds. So it observes, it appears like a solve this into, if you resolve this into T space, it appears like almost a single tap, at most a second tap may occur. Okay. Okay. Coherence time we understand, right? The time separation at which the fades become statically independent. There is what is called coherence bandwidth. That is the frequency separation at which two frequencies become statistically independent. That means I send it F1 and I send it another tone at F2. The frequency separation at which two tones become statistically independent. What does that mean for the wideband channel model? We have, remember, h of tau, the impulse response. What was this? Minus tau n, something like that, tau minus tau n. Okay. And h of f is Fourier transform of h of tau, and let us plot h of tau. If I take 200 kilohertz bandwidth, maybe the channel looks nearly flat. If I take the inverse of this, then it will end up with a one single tap if it is flat. But if I take 5 megahertz, then different frequencies will go through different attenuations, and at some point you may have a null and a peak. So that kind of can be, that sort of can be perceived as some form of frequency diversity. Multipath gives you frequency diversity. Delay spread gives you time diversity, because at sufficiently long time intervals, if you repeat your data, you will get diversity. Delay spread gives you time diversity. Multipath delay spread gives you, Doppler spread gives you time diversity. You may be wondering what is diversity, but that will come. And delay spread gives you frequency diversity. So the same frequency diversity can also be viewed in time domain if you resolve them as independently faded taps. The impulse response, if there is a lot of, if they are statistically independent these taps, then you can build an equalizer to capture diversity from these way of looking at it. Or you can view it in the frequency domain. Different frequency components go through different fades, and if you use OFDM and if you code across this data, you can also so far I think we'll conclude this here. We did cover pretty much the basic characteristics of wireless channel. We talked about relay fading, we talked about long-term fading shadowing, we talked about Doppler spread today, and we talked about delay spread, but we didn't call it delay spread in the previous lecture. We just assigned a arbitrary long impulse response, and then we decomposed into T space, and then we talked about narrow band and wide band, right? Narrow band and wide band systems. And if the delay spread is very small, it can become, compared to the signal inclination, it can become narrow. So what I want you to do is, next week you should submit the simulation of the Jakes model and the autocorrelation function, and take some calculations on what is the Doppler spread? What is the point? Doppler frequency, what is it? In fact, you can take two samples taken from the JX model and you can check whether they are statistically independent. Samples taken at, let us say, tau apart. Then you can take a sequence of samples and check if they are statistically independent. Okay, and I want you to plot the PDF of the envelope of PDF of envelope of P. How would you do that? Well, collect as many time samples as you can, but take them far apart. If they're too close, then take them far apart and use INF Doppler and plot the PDF of PF. And what should be the distribution? Really, right? Envelope should have really distribution. Take the time samples